Hello. In the previous video in the series of the Laplace transform, we had discussed about the unit step function. We'll try one more numerical related to the unit step function with the question that you can see on your screen, and then we'll move over to the second shifting theorem. Now this question, it asks us to express the following function that has been provided in terms of the unit step function, that is f of t is equal to t minus 1 for t lying between 1 and 2, and equal to 3 minus t for t lying between 2 and 3, and also we are to find its Laplace transform. Now for the given function, what we can write, as you might have come across the case of the unit step function in the previous video, then we have this expression, this function that we have at hand. We'll be expressing that in the following manner, that is t minus 1, and then we have the unit function of t minus 1 minus the unit function of t minus 2, and then we add it up with the second case for t lying between 2 and 3, that is I'll write it in the next line. So 3 minus t times of the function of t minus 2 unit function, and minus the unit function of t minus 3. So that's how we put it in the range, and that would give us eventually t minus 1 times of the unit function of t minus 1. So we open that up, we provide that in the distributive multiplication that we will be doing here. So t minus 1 times of u t minus 2, and then plus 3 minus t times of u of t minus 2, finally minus of 3 minus t times of u of t minus 3. With all of that, in the next line we have t minus 1 u of t minus 1, and we put the value over there, that is we bring the common term that we have, t minus 2 and t minus 2, so u of t minus 2, and then if we evaluate minus of t minus 1 and 3 minus t, so we get 3 minus t minus t, which is 3 minus 2t, and plus 1 is 4 minus 2t, so we can get the common term as plus of 2. 4 minus 2t means t minus 2 with the 2 taken outside, and we have u times of t minus 2, and then the final expression that we have, that is we can just interchange that. We can put it as instead of 3 minus t in the negative, we can put it in the plus. We apply that minus within that bracket, so that is t minus 3 u of t minus 3. So that is our expression. Now if we wish to try the Laplace transform, then the Laplace transform, so this is f of t, so the Laplace transform of f of t in this case is going to be equal to e raised to the power minus s divided by s squared, following the rule of the Laplace transform, 2 times of e raised to the power minus 2s over s squared. All of those rules have been discussed in the previous video, so you can just refer to that in case you haven't understood this. So you can refer to that video and the rules that are associated with it. Now the second shifting theorem that deals with the unit function. So if we have the Laplace transform of f of t as f of s, which is what we have, then we can write it as the Laplace transform of f of t minus a times of the unit function of t minus a, and that will be equal to e raised to the power minus as times of f of s, where f of s obviously is the function that I have provided right from the very beginning. So we will try and prove that. We can prove that. So as far as the proof is concerned, we'll first start off with the left hand side. So the Laplace transform of f of t minus a times of the unit function of t minus a, that is equal to, if we put it in the by definition of the Laplace transform, so we have e raised to the power minus st, and the term that is to be transformed, we have that over here, that is f of t minus a, and then u of t minus a, and all of that times of dt. Now we take it one by one. So the limit for the function t minus a, what we can do over there is we put it from 0 to a. Now because it is within that a, so the function as per the definition of the unit function, f of t minus remains t minus a remains as such. But what about u of t minus a? Well, that is simply 0, because that is how we define the unit function. And then for values above a, we'll be having we can take it from 0 to infinity. It doesn't really matter because we are concerned about the limits. Within a, it is going to 0, so it doesn't really matter if we are taking from 0 to a and then from a to infinity. We'll keep it as 0 to infinity. E raised to the power minus st f of t minus a, and the value of u of t minus a is going to be 1 as per the definition of the Laplace transform, and as per the definition of the unit function. So with that, what we get is this is equal to simply 0 to infinity, and we can try a few things over there. Instead of t, we can put u plus a, and so we have f of t minus a as u plus a minus a, so that is f of u, and dt becomes du. We have used t to be equal to u plus a. That is what we have used over here. That really doesn't change the limits, neither does it change the value of the other values. The values that have been changed have been placed over there, and that will simply be equal to, well, we can take out the e raised to the power minus s a, and from 0 to infinity we'll be integrating e raised to the power minus su f of u du, and this is nothing but the Laplace transform of f of u instead of f of t. But again, that would give us the same capital F as a function of s. So this is e raised to the power minus sa f of s, which is what we had given in the theorem. So that's the second shifting theorem. Now what if we had the function, that is, we were to consider the Laplace transform of f of t times of the unit function of t minus a. Now in that case, the things would have been as they have been in this derivation. This, I would like you to consider this line over here. In this line, what we get is that we are trying a variation with t, that is, t is equal to a substitution, rather t is equal to u plus a. So t is equal to u plus a in that case. Then we have e raised to the power minus s times of u plus a. Now that bracketed term over that function, that is f of, had there been t minus a, we are getting f of u. But for only f of t, we would have obtained the value of t, that is that which we are substituting, that is u plus a. So f of u plus a du. So that would have yielded the final expression as e raised to the power, well, let me write that. I'll be proving this one from this step. So I'll be using that over there. So that is f of, so this is e raised to the power minus s, and we are using the same thing, that is u plus a supposedly. So u plus a, and then we have f of u plus a du, u plus a du, and that is giving us e raised to the power minus s u, that is sa, that is going outside. And then we have the integration from, obviously, from 0 to infinity, and we are keeping e raised to the power minus su f of u plus a du, and then in the final step what we are getting is e raised to the power minus sa times of the Laplace transform of f of s plus a. So this is not s plus a, that is t plus a. Because we have the u as a dummy variable, so we can just replace it by t, and we end up with the Laplace transform of t plus a. So that's the theorem that is associated with the unit function, that is the second shifting theorem. We'll try a few numerical valued problems related to that, and then we'll move over to the next part. So with that, we are to try this question, that is to find the Laplace transform of t squared times of the unit function of t minus 3. So in that case, we'll just express this. So the expression that carries is t minus 3 squared plus 6 times of t minus 3 plus 9 all multiplied with u of t minus 3. There is actually nothing to be worried about that square bracketed term, because that is just t minus 3 plus 3 whole squared instead of that t squared. The reason why we have done that you will see in a short while. So let me just write that in case you are having any confusion with it. So this is t squared. I can write t simply as t minus 3 plus 3, and then I can square it up. It's the same thing as t squared. So this is t minus 3 whole squared plus 2 times of 3 times of t minus 3, and then plus 3 squared is 9. So 2 times of 3 here is 6. So 6 times of t minus 3, that is what we have got over here. Now with that, what we get is we open the brackets, so we multiply the unit function with all of them. So t minus 3 whole squared times of the unit function of t minus 3. Then we have plus 6 times of t minus 3 multiplied to the unit function of t minus 3, then plus finally 9 times of the unit function of t minus 3. Now with the Laplace transform of t squared times of the unit function of t minus 3, we get this as the Laplace transform of the first term, of the second term, and of the third term. So we write that individually. We'll do a bit of writing over here. So this is t minus 3 whole squared times of u of t minus 3, then followed by the Laplace transform of, well, the 6 can be kept outside, Laplace transform of t minus 3 u times of t minus 3, and that's actually the unit function of t minus 3, and then finally we keep the 9 outside and the Laplace transform of the unit function of t minus 3. Now, as per the rules that we have studied, we will be getting for t minus 3, we'll be getting e raised to the power minus 3s, following the shifting theorem that we have studied, that is e raised to the power minus of as. So instead of a, we have 3 over here, so e raised to the power minus 3s. And as for the Laplace transform of the unit function, the values that have been multiplied over there, so for the squared term we have 2 over s cube, and then 6 over s squared, finally 9 over s, because of the theorem of Laplace transform of the unit function e raised to the power minus as divided by s. In those cases, the value of s, the powers of s, that is, we have, so we have used the shifting theorem, of course. Now this is one way, so there's another way of doing it as well. So if we consider this case, that is the Laplace transform of t squared times of the unit function of t minus 3. So instead of t, what we can use is we can use another variable. That's just the way to do it. That is, we can try t to be equal to supposedly k plus 3, suppose. So we take t is equal to k plus 3. What that means is that we will be doing the Laplace transform of k plus 3 squared, and the unit function, so u of k plus 3 minus 3, is going to be simply k. Now k means k minus 0, and as per the definition of the Laplace of the unit function, with the integrations involved, the Laplace transform of that would lead to nothing. It'll be completely, just value will be equal to 1, which is nothing but the second theorem of the which will lead to the second theorem of the second shifting theorem. So what we do is we simply have this as the Laplace transform of k plus 3 squared, and as far as the second shifting theorem is concerned, we will be having e raised to the power minus 3s over here. So that would give us e raised to the power minus 3s times of the Laplace transform of t square, not t square, k square plus 6k plus 9, and all of that we'll have e raised to the power minus 3s. And from the Laplace transform, the general formula, we have 2 over s cube plus 6 over s squared plus 9 over s. And in case you have any confusion with this step, you can just refer to the second shifting theorem, the second case of the second shifting theorem, where we have the Laplace transform of the function of t times of the unit function of t minus a, and that is simply equal to e raised to the power minus as times of the Laplace transform of the function of t plus a. So instead of t, I have used k, so there's a slight difference in that with the, if you look at the variable, but that's a dummy variable, so we need not be concerned about that. We can use this directly. This was just a way of showing how it's done. Now in the next bit, we are to determine the Laplace transform of the function e raised to the power minus 2t, that is the exponential of minus 2t times of the unit function pi of t. Now unit function pi of t is defined as shown, so that simply means that we have this as u of t minus pi, and for the Laplace transform of e raised to the power minus 2t, that means f of t here is e raised to the power minus 2t. So what will be f of t plus pi, because we are going to use the second shifting theorem. So f of t plus pi is simply going to be e raised to the power minus 2 times of t plus pi. So with the use of the transformation or the substitutions, the second shifting theorem. So we have e raised to the power minus pi s times of the given Laplace transform. So the Laplace transform of e raised to the power minus 2t u pi t is simply going to be e raised to the power minus pi s times of the Laplace transform of f of t plus pi. We already have the value of f of t plus pi. We are going to use that. So that is going to be e raised to the power minus pi s times of the Laplace transform of e raised to the power minus 2 t plus pi, and we can take the 2 pi out, and we have simply e raised to the power minus 2t within that Laplace transform. So we have e raised to the power minus pi 2 plus s, the 2 coming out, and the Laplace transform of e raised to the power minus 2t will simply give us from the first shifting theorem, that will give us 1 over s plus 2. So that is our answer for the given bit, that is the Laplace transform of this. So we are using the first shifting theorem over here and the second shifting theorem over here. Now we can discuss a few more theorems related to the Laplace transform. So first of all, we have the convolution theorem, which tells us that if we have the Laplace transform of f1t to be equal to f1s, that is the capital F1s, and the Laplace transform of f2t to be equal to capital F2s, then for the Laplace transform of taken from 0 to t, f1x times of f2t minus x dx, that is going to be equal to the capital F1s times of the F2s. That means the Laplace transform of f of f1t, f2t multiplied together. So that's the convolution theorem for you. And as for the Laplace transform, I'm providing you with the formulas now without the proof, because they are going to be used just to solve the numerical problems. So the Laplace transform of the Bessel function, the popular function Bessel functions, let's take the case of j0 x and j1x. And for those two, what we have is, instead of x we may use t. So the Laplace transform, in the first case, the Laplace transform of j0 t is equal to 1 over s squared plus 1 under root. If we have a times of t, that is the Laplace transform of j0 at, then we have this to be equal to 1 over s squared plus a squared under root. And then as for the Laplace transform of j1 x or t, you choose the variable, so that is going to be equal to 1 minus s over s squared plus 1 under root. So these are the formulas that are associated with the Laplace transform of the Bessel functions. And then we are trying to use the Laplace transform to some good effect, so we'll see how they are helpful in solving the integrals. So if we consider the cases of a few integrals which usually have the lower limit as 0 and the upper limit as infinity, so let's take the case of supposedly t times of e raised to the power minus 3t sine t dt. So this is nothing but the Laplace transform of instead of s we have 3 over there, and this is the Laplace transform of t sine t dt. Now this, the Laplace transform of t sine t, we know t raised to the power n, f of t is going to give us a minus 1 raised to the power n, in this case that being equal to 1. And then we have the nth order derivative, and so we are taking the first order derivative over here with respect to s of the function f of t. Now f of t over here for sine t, we are going to have 1 over s squared plus 1 for that sine t, and this result is going to give us this value. This calculation is going to give us 2s over s squared plus 1 whole squared, the negative taken care of with the derivative done. And now s has the value of minus 3 over here, because that is minus s e raised to the power minus st. So s has the value of 3 over here. So this integration is going to give us 2 times of 3. Instead of s we are putting 3 over there. So this is 3 squared plus 1 whole squared. So this is simply 6 over 100, or you can take it as 0.06 or 3 by 50, anything you like, but that's the answer. So this is a way in which you can carry out the integrations, especially with the lower limits being 0 and the upper limits being infinity, and they are very the Laplace transform is very useful in carrying out these calculations pretty easily than other really precarious calculations that you may think of. So that's it from this video. We have completed the case of Laplace transform. We will be looking at the inverse Laplace transform and how we are going to use it to good effect. It would be ideal that you try out various numericals related to the Laplace transform that have been provided, and if you have any doubts regarding that, you can place them and we'll try and evaluate them. Till then, thank you for watching.